Hi everyone, this is 3.3 for Calculus 1, and this is derivatives of trigonometric functions. And first we're going to start off by finding derivatives of sine and cosine. From there we can find the derivative of any trig function, as it turns out, because of course if you remember from trigonometry you can write any trig function, tangent, cosecant, secant, cotangent, any of them, in terms of sine and cosine. So these are the building blocks of all trig functions. So finding the derivatives of these will help us find derivatives of all of them. And to do that, we could do it by definition of derivative, and it just requires a few properties of trig functions. Basically, you'll need the summation formula, the addition formula for sine, also for cosine, and you need to use some limit properties as well. I may talk about some of the limits later on, but for right now, I'm going to actually prove the derivative of sine and cosine for you from a graphical perspective, which isn't the most rigorous way, but it's enough for us for right now. But again, if you want to try the definition of derivative way, it's a little more rigorous and convincing. You can try that on your own, but you will need those things I mentioned. So all I'm going to say is this. So these are the graphs of sine and cosine, respectively. And if you consider their tangent lines for particular points, obviously there's infinitely many points on this, so there's infinitely many tangent lines for each point, one for each point. But what I'm going to do is I'm going to actually look at where you get zeros. So where are the tangent lines 0? First, let's do one at a time. So let's do a sine first. So when is the slope of the tangent line 0? So let's see. It's 0, it looks like here and here. So notice what I'm doing is I'm plotting a x-intercept at these points because that's when the slope is 0. So if this is y, this is going to be y prime, and we're going to see what the graph looks like. Also notice before here, it seems to be positive. So if you pick any point on the function here, and you were to graph the tangent line of that point, then it's a positive slope. So it goes up, meaning that the y prime value is going to be above the x-axis. So it's going to be positive, something like this. Okay. Similarly, from here to here, picking any point, it's decreasing, so its slope would be negative. So that would be down here. And then back here, any point on this side of the graph, making a tangent line, will make it positive. So notice what we get is something that coincides with what looks like the graph of cosine, actually. So this is going to be cosine of x. Now again, that's not a very rigorous explanation, but it's enough for us for right now. If you look in the book, they show both, actually, which is kind of nice. But usually people kind of take my word for this. But let's move on and see what it looks like for cosine. It's a little different. So for cosine, again, we want to make sure these points kind of correspond to the same. So imagine this is 0. This corresponds to 0. This corresponds to 0. Between here and here, the slope is negative, so we're below the x-axis. Any point here to here, the slope is positive, so that's above the x-axis. And notice, this doesn't quite look like the graph of sine for y prime in this case. It looks like the graph of sine if it was flipped, and to flip something across the x-axis, you just multiply it by negative, so this will indeed be negative sine of x. So now that we have somewhat of an understanding, or at least me convincing you, I guess, that these are the correct derivatives of sine and cosine, we can move on and find all of the other derivatives for the other trig functions. So let's see that right now. Okay, so now moving on, I'm going to do 2 here and then 2 in the next screen. But I want to find the derivative of tangent and then the derivative of secant, and I'm telling you what they are. Tangent has derivative of secant squared. Secant has derivative of secant tangent. To see this, we'll need to see a few things, but first I want to recall some trig identities. And those, of course, are tangent and sine over cosine. Secant is 1 over cosine, and the one we know and love, the Pythagorean identity, sine squared plus cosine squared is 1. The other thing I want to use here, of course, will be the quotient rule, because for proving tangent, we want to write tangent as sine over cosine. So now to find the derivative of sine over cosine, well, we need to find the derivative of this quotient, so we need to use the quotient rule. So it's going to be all over the bottom squared. And let's see, what do we have on top? Well, it's going to be derivative of the top, which is cosine, times regular of the bottom, minus regular of the top, which is just sine, times derivative of the bottom. So let's recall, what is derivative of cosine? It's negative sine. Good, glad you remembered. We just saw that. So notice, here cosine times cosine is cosine squared. Here, sine times sine is sine squared. There's a double negative, so it's positive sine squared. Aha. So what does the top turn into using this Pythagorean identity? That's right, it's just 1 because cosine squared plus sine squared is just 1. So we get 1 over cosine squared. And remember, cosine squared just means cosine all squared. So 1 over cosine all squared is, well, just 1 over cosine all squared. So basically you can use some power properties to write it like this, but that's kind of a step you can, I guess, skip, really. Because this would be secant all squared, because 1 over cosine is secant. So that is secant squared of x. Awesome. Done. And now I'm going to prove the one for secant, but I need more space. So let me erase this, and we'll do that right now. Right, so the first place I want to start off with, of course, is that secant is 1 over cosine. So now we can, similar to how we did tangent, we're going to apply the quotient rule. To find the derivative of this, it's going to be all over cosine squared, derivative of the top, which is 0, times regular of the bottom, minus regular of the top, 1, times derivative of the bottom. Derivative of cosine is negative sine. Perfect. So 0 times anything is 0, so ignore that term. Negative times negative is positive, so that's positive sine over cosine squared. And yes, we are going to somehow rewrite this as secant times tangent. Here's what we're going to do. We're going to split this up as 1 over cosine times sine over cosine. Why would we do this? Well, because of course the top is 1 times cosine, the bottom is cosine times cosine. So if you multiply straight across, you indeed get sine over cosine squared. Also, notice 1 over cosine is secant, and sine over cosine is tangent. Yes. So it is indeed secant times tangent. Like I said, it would be over there. So that finishes off that proof. And now we're going to see the other two that I've left off, which are the derivatives of cotangent and cosecant. So let's see that right now. Alright, so first off, this is going to look very, very, very similar to what we just saw from the previous two. So it's nice to see the reinforcement of the knowledge. But at the same time, there's a nice pattern that happens based on what we saw. In fact, most people don't remember these two. Most people just remember the ones I just showed you. Tangent goes to secant squared, and secant goes to secant times tangent. Why is that? Well, if you know that tangent goes to secant squared, then you can just remember that for the co-version of those, you just get negative of that. Kind of like how derivative of sine is cosine, but derivative of negative cosine is positive sine. So think of it like this. If derivative of tangent is secant squared, then derivative of cotangent is negative cosecant squared. Similarly, derivative of secant was secant times tangent, derivative of cosecant will be negative cosecant times cotangent. So just hit everything with a co, but as a consequence you get a negative. So just keep that in mind. And now, well, let's see, using again the quotient rule. Now I changed these a little bit. Cotangent is cosine over sine this time, and cosecant is 1 over sine. So let's see what we get. We get all over the bottom squared, derivative of the top, which is negative sine, times regular of the bottom, minus regular of the top, times derivative of the bottom, and derivative of sine is cosine. So notice what we get here on top is negative sine squared, negative cosine squared. If we pull a negative out of that though, well, we get sine squared plus cosine squared. All over sine squared. And yes, sine squared plus cosine squared again is 1. So this is negative 1 over sine squared. As we saw previously, 1 over cosine squared was secant squared because 1 over cosine was secant. Similarly here, since 1 over sine is cosecant, 1 over sine squared is going to be cosecant squared, but since it's negative, it's going to be negative cosecant squared. Perfect. That proves this one, and I'm going to erase this and prove cosecant's derivative to you. Alright, so let's see. Cosecant is 1 over sine. Perfect. Find derivative using quotient rule. It's going to be all divided by the bottom squared, by sine squared. Derivative of the top, which is 0, times the regular of the bottom, which is just going to amount to 0, by the way, minus regular of the top times derivative of the bottom. Derivative of sine is cosine. So we end up with altogether negative cosine over sine squared. And also, as we previously did with derivative of secant, we're going to split this up in a pretty clever way. I'm going to split this up as, well, negative first off. 1 over sine of x times cosine of x over sine of x. And you can see if you multiply straight across, you indeed get this. And yes, 1 over sine is cosecant. Cosine over sine is cotangent. And it's negative. So we indeed get what I said we would get. Cosecant times cotangent, but negative that. Negative cosecant cotangent. Great. So now we'll see some examples using these rules. Alright, now here for some really fun examples. They're all kind of involved, to be honest, but let's see. So we want to find the derivatives of all of these, keeping in mind those rules we saw. I don't have space to list them. We can go back and write them down if you'd like, but yes, I'll just say them aloud, I suppose. Sine goes to cosine goes to negative sine, tangent goes to secant squared, secant goes to secant times tangent, cotangent goes to negative cosecant squared, and cosecant finally goes to negative cosecant times cotangent. Wow, okay, good. So let's see. So here, this is x times sine of x, so we have to use, well, we'd have to use actually product rule. So derivative of f would be, well, regular of the derivative of the first, regular of the second, plus the other way around, regular of the first, x times derivative of sine, which is cosine. So this is just, well, 1 times sine is just sine. So it's sine of x plus x cosine of x. And that does it for number 1. It wasn't too bad, not really much combined, so we're lucky there. Next, here, let's see what happens. Again, it's times, it's a product, e to the x times cosine of x, so we have to use product rule. So here y prime is going to be derivative of the first, which is e to the x, times regular of the second, which is cosine, plus derivative of, well, I mean to say regular of the first, which is e to the x, but they're the same, so we got lucky here. And then now times derivative of the second, which is negative sine. Okay, I'm going to change this a little bit just because of space. The first one is good, it's the same. Here, e to the x times negative sine of x is just negative e to the x times sine of x. So I'm just going to change it like that. Good. And that's the answer there. Nothing combines. They are not like terms even though they share e to the x. In fact, if you wanted to, you could pull out e to the x and then inside parentheses, you'd have just cosine of x minus sine of x. Here, we want to find the derivative of f of theta is tangent theta over theta. That'll require a quotient rule. So let's see, we're going to get f prime of theta is, let's see if we can do it, all over the bottom squared. Good. All right, say it with me. So we have derivative of the top, secant squared. Times what? Regular of the bottom. So that's times theta. Okay. Minus regular of the top, tangent, times derivative of the bottom, which is 1. Derivative of theta is 1 with respect to the variable theta. Very good. There's not really much we can do here, but I am going to rearrange things a little bit. Theta, I'm always going to write in front. And the reason why I'm going to write it in front is because it looks like these thetas will multiply, but they don't because this is technically secant squared of theta, not multiplied by theta. So this theta that comes after the secant squared doesn't play with anything that's multiplied outside of that function. So for that reason, I'm going to move this in front, if that's okay. Alright, so this is going to be theta times secant squared of theta minus tangent of theta all over theta squared. And there's not really much we can do here as far as simplification goes, so we're kind of stuck. And you may think, oh, don't these thetas cancel out? They don't, because only if we pull theta out from the entire top, then we can cancel out a theta with the bottom. But this second term doesn't have theta in common. Okay, so now for this next one, this is a quotient, so we need quotient rule. But there's a product on top, so you need to do a product rule within the quotient rule. Let's see if we have space. I believe we do, but let's see if we can figure it out. So it's going to be applying the quotient rule, because it is a quotient. We're going to do all over the bottom squared, 1 plus t quantity squared. Derivative of the top, this is where we need to apply product rule. So we'll do derivative of the top right now, and then times regular of the bottom, 1 plus t, okay, minus regular of the top, which is t sine of t, okay, times derivative of the bottom. And derivative of 1 plus t is 0 plus 1, so that's times 1. Just like that. Now I left this blank because we're going to need to do a product rule to find the derivative of t times sine of t. But guess what? We already did it coincidentally. Only this is with x's instead of with t's, but the answer is the same. So the derivative of t sine of t would be sine of t plus t times cosine of t. Sine of t plus t times cosine of t. There we go. Barely have enough space. And should we distribute things on top? I think we should. Let's see. So let's distribute sine into each of these, and then t cosine of t into each of those. This is just negative t sine of t, and let's see what we get. Again, I think we have space. I made it to squeeze things up in here a little bit, but let's see. It's going to be all over 1 plus t squared. And on top, it's going to be, let's see, that's going to be sine of t times 1, so sine of t, plus t sine of t. Okay. And then now for t cosine of t times 1, that's plus t cosine of t. And then t cosine of t multiplied by t, that's going to be t squared cosine of t. And now finally minus this t sine of t. And notice the cancellation we get. We get that the t sine of t's cancel out, just like this. And all we have left on top is sine of t plus t cosine of t plus t squared cosine of t. So that's sine of t plus t cosine of t. Trying to make sure these t's don't look too much like pluses, so I try to curve the bottoms. Plus t squared cosine of t. And that's of course all over 1 plus t squared like this. And that is the answer there. Nothing more can be simplified. So we'll leave it like that. And I want to do a few more examples. Alright, so now the next few examples I want to do will be a little bit different than ones involving derivatives of trig functions. They'll still involve those a little bit though, but they're less find the derivative of and more special, I guess you can say. So this one asks us to find the 99th derivative of sine of x. Now, well, first let's notice a few patterns. So first I'm going to start with sine. Now let's just keep track of things. Let's call it y. And we'll find y prime. That's going to be cosine. Derivative of sine is cosine. Now let's find one more derivative. Let's call that y double prime, just means second derivative. Derivative of cosine is negative sine. So we're going to keep taking derivative of the previous theme, basically. And now can we find y triple prime? Well, let's see. Y triple prime would be negative, well, derivative of sine is cosine, derivative of negative sine would then be negative cosine. Because of the constant multiple rule, this is negative 1 times sine, so its derivative is negative 1 times whatever derivative of sine is, which is cosine, so it's negative cosine. And now finally, for the fourth derivative, what we do sometimes if we run out of space for primes, like if you were to imagine writing this as y and then 99 primes, it's way too difficult. So we write the number of primes in parentheses. So here y4 in parentheses means y quadruple prime. So that's going to be, well, let's see. Derivative of cosine is negative sine, so double negative is positive sine. And notice, you go from here to here, here to here, here to here, and then you could say here to here, but sine of x is just the same as y. So as it turns out, we get back here and now we're stuck in a loop. Which is nice, because this will allow us to figure out what the 99th derivative of sine is. And in fact, one way to think of this is that every fourth derivative is sine when you start with sine. So the eighth derivative, well, if you just count, so it's going to be first derivative, second derivative, third derivative, 4, 5, 6, 7, 8. So every multiple of 4 derivative would be back to sine. So if you wanted to find the 100th derivative, it would be sine. The one before the 100th would be the 99th, so that would be negative cosine. So there's some logic here, of course, but it just has to do with the fact that the derivative of sine is this has a cyclic relationship, basically. So the answer here is going to be negative cosine of x. Alright, so now for the next example. Okay, like I said, this example is a little different. So it asks us to find a and b, so constants a and b, such that y equals a sine plus b cosine satisfies this equation here, y double prime plus y prime minus 2y is equal to sine of x. This type of equation, by the way, is called a differential equation. Differential equation is just an equation involving derivatives of a function, and the goal is to find the function. In this case, they gave us the solution to this, so it would be a sine plus b cosine, but they didn't tell us what a and b were. It's up to us to figure that out. So the way I'm going to do this, I'm going to look at the solution to the differential equation, and I'm going to plug it into the left-hand side here. So I already have y, so we need negative 2y. So let me write that. Negative 2y is equal to negative 2a sine of x plus, well, I guess negative 2 times b cosine of x. That's negative 2y. Now what's y prime? Y prime is the derivative of y. A and b are constants, so we just need to find the derivative of sine and cosine. So derivative of sine is cosine, so it's a cosine for the first term. Derivative of cosine here is negative sine, so it's going to be negative b sine for the second term of y prime. Alright? Now for y double prime, this is the other term we need for the left-hand side. We need the second derivative, which is just derivative of each of these terms. Again, a and b are constants, so they're going to come down for free. Derivative of cosine is negative sine, so it's negative a sine of x. Derivative of sine is cosine, the sine will stay the same, so negative b times cosine. Perfect. And now what? Well, now it says y double prime plus y prime minus 2y prime. When you add those together, you get sine of x. So let's add all of these together and see what we get. There are some like terms, some of them aren't like terms. Here's what I'm going to do though. I'm going to group all of the signs together. So that's a sine and that's a sine. So all times sine of x, here's what we're going to have. All times sine of x, we're going to have negative 2a, leave a little more space, minus b, minus a. So if you add these terms together and pull out sine of x, you'll have this on the inside. And notice these two combine to negative 3a and then minus b times sine of x. Similarly, for the cosines, let me just show that in red, I guess. We're going to have these three. So if we pull out cosine that they all have in common, we'll have plus some quantity of terms multiplied by cosine of x. And those are in order, negative 2b, a, and negative b. And those, of course, combine to negative 3b, but let's write a minus 3b, I guess, times cosine of x. Now, great, that's adding all of these terms here on the right, but what do these on the left add to? Well, on the left, what we've constructed is this. And since y double prime plus y prime minus 2y is equal to sine of x, this whole thing here must be equal to sine of x. And what must these coefficients end up being? Well, actually, they must be the following. Notice this is 1 times sine of x. There are no cosines, so if you wanted to, you could write this as plus 0 times cosine of x. Meaning, this is going to be 1, and this is going to be 0. So now we'll just solve a system of equations to actually find out what a and b are. Alright, so now I'm just going to solve the system real quickly. I'm going to do this by substitution. So notice in the second equation we can find a by adding 3b to the other side. So a is just 3b. Plugging that into the top equation gives us negative 3 times 3b, because a is equal to 3b, minus b is equal to 1, these multiply to negative 9b. Negative 9b minus b is negative 10b is equal to 1. Dividing by negative 10 gives us that b is negative 1/10. Good. Since a is 3 times b, then these both imply that a is equal to negative 3/10. And there we go, that's our answer here. So these a and b values are the values that will satisfy this solution that satisfies this differential equation. Now I know this was a little bit outside of the scope of 3.3, but it is an example in the book. I mean, it's in the book somewhere, is what I'm trying to say. It's an exercise in the book. And it does involve derivatives of sine and cosine, which is why I wanted to go over it. I know it's a little far off, but it's still a nice application which I feel we deserve to see. So now for some limit problems, like I said we would probably talk about earlier, and here they are. We need to discuss this one before we can see this one. So we're going to be using some idea that this shows to actually solve the next example. This is a very difficult problem, honestly, to just do on your own. One way to do it is by plugging in numbers close to 0. If you plug in, like, let's say 0.0001 to each of these x values, you'll get that it'll be something close to 1. So by numerical approximations using your calculator, on either side of 0 actually, so a positive number close to 0 or even a negative number that's close to 0 will give you about 1 as your answer. So you can guesstimate that this is 1. But what I'm going to do instead is I'm going to show you something that's a little different. So here's what we're going to do. Consider the derivative of sine. So f of x is sine of x, f prime of x is cosine of x. We know that much. Now using the definition of derivative though, f prime of x is going to be the limit as h goes to 0 of sine of x plus h minus sine of x all over h. That's the definition of derivative for sine of x in particular. Okay, now what? Well, what if x is 0? So if x is 0, here's what we get. We get f prime of 0 is equal to the limit as h goes to 0 of, on the top, we'll have sine of 0 plus h, so that's just going to be sine of h actually, minus sine of 0. What's sine of 0? I hear you screaming it out. Sine of 0 is 0, yes. So this is just 0, so I'm just going to not write anything because anything minus 0 is itself, all over h. And look at that. This right here we have on the right hand side is exactly what we're trying to find, only with x's instead of h. This is equal to f prime of 0. F prime of x is cosine, so this has to be cosine of 0, which is 1. So the answer is 1. Good, so it coincides with our guess. So the answer here is 1 for maybe unobvious reasons. Now we're going to try to use this to solve this problem. And it's not obvious. But what we're going to do is we're going to make this happen, to make this appear, we need sine over theta instead of sine over this. So what I'm going to do actually is I'm going to divide top and bottom by theta. So multiply this by 1 over theta, multiply this by 1 over theta. So what we end up getting on top is sine theta over theta. On top. On the bottom, well, if you distribute this 1 over theta, we get theta over theta, which is 1, plus, I would write tangent of theta over theta, but I'm going to do something a little different. I'm going to remember that tangent is sine over cosine. So sine over cosine times 1 over theta, if you rearrange things a little bit, you can write this as the following. As sine over theta times 1 over cosine of theta. Now we're going to apply the limit as theta goes to 0. So there are a few kind of technicalities here, but we're basically using limit laws to say that we can apply this limit to each term here in this quotient so long as the limits exist. And these do. And the other one does as well. So if you plug in theta equals 0 into each of these, well, the limit as theta goes to 0 of sine of theta over theta, just like we saw from the previous example, is 1. So each of those things in red parentheses is going to turn into a 1. So now what we're going to be left with is 1 over 1 plus 1 times, and now we need to figure out what this goes to as theta goes to 0. And yes, it is a direct substitution actually. If you substitute 0 in directly, you get 1 over cosine of 0, which exists. Cosine of 0, as we saw here, is 1, so 1 over 1 is 1. This is just going to approach 1. So that's going to be 1 over 1 plus 1 times 1, which is 1 over 1 plus 1, which is just 1 over 2. Perfect. And I want to do one more limit example. The next limit example will actually not involve derivatives at all, but I think it's going to be a fun thing to see. It'll use some trig properties, so let's see if we can see that. Okay, so like I said, I don't think this one actually involves derivatives. You can probably try to figure out a way to involve derivatives in this problem, but I don't think we need it. In fact, all I'm going to do is get rid of tangent and write it in terms of sine and cosine, so I'm going to do that right here. Tangent was what again? It was sine over cosine. Now I'm going to rewrite this 1 as 1 over 1 so that we can combine these on top into one fraction. So if you multiply top and bottom of this 1 over 1 by cosine of x, you end up getting what? Well, on top, you'll get cosine of x minus sine of x, so let me write that. Cosine of x minus sine of x, all over their common denominator, which is just cosine. So the numerator, what was 1 minus tangent of x, turns into this. This, of course, is all over sine of x minus cosine of x. Do we see what we can do? The denominator is sine of x minus cosine of x, we can write as a fraction in its own right, over 1. And then since we have a fraction over a fraction, we can just simply multiply the top by reciprocal of the bottom. Cosine minus sine and sine minus cosine are negatives of each other, so when you divide them you get negative 1. I'll show that right now. And we're still in the limit, of course, as x goes to pi over 4. So let me write this. So we have limit as x goes to pi over 4 of the top, which is cosine of x minus sine of x, over cosine of x, times the reciprocal of the bottom, which is 1 over sine of x minus cosine of x. And to show that when you cancel them out, you get negative 1, let me do this with the top. I'm going to pull negative 1 out. So if I pull a negative outside from this, I change the signs of each of those terms. So in fact, it should turn to this really. Okay, there we go. So I have negative outside of negative cosine of x plus sine of x. You can check this by distributing the negative back in, and you'll indeed get cosine of x minus sine. Notice you'll get a double negative for the first term, leaving you with positive sine, and negative sine of x for the second term. Perfect. Now, negative cosine of x plus sine of x is the same as sine of x minus cosine, so these will cancel out. So all we're left with now is negative 1 over cosine of x. When you plug pi over 4 in, you actually get a value. You get negative 1 over cosine of pi over 4 is radical 2 over 2. So this is just negative, well, the reciprocal of, so remember how it works again. The top is technically as a fraction, negative 1 over 1. Again, we have a fraction over a fraction, so multiply top by reciprocal of the bottom. So altogether this is negative 2 over radical 2. If you want to rationalize it, you can multiply top and bottom by radical 2, which I encourage everyone to do, because in this case, radical 2 times radical 2 is just 2, and the 2's cancel out. So radical 2 times radical 2 is just 2 itself, the 2's cancel, so altogether the answer is just negative radical 2. Again, this example, the way I showed it anyways, involved no derivatives, but it was a nice application of limits using some trig properties, which I think was nice. I really hope you enjoyed this section. There's a lot of fun stuff we saw here in chapter 3.3, and I'll see you in the next videos for 3.4, 3.5, and the rest of chapter 3 basically. See you then. Thanks for watching.